When Pluto was redefined as a dwarf planet in 2006, it marked the end of an era in our solar system's understanding. Once considered the ninth planet, Pluto's demotion left many perceiving it as a cold, desolate rock on the edge of the solar system. However, recent declassified images from the James Webb Space Telescope have completely overturned this idea, revealing an entirely new and baffling reality. What these photos reveal is nothing short of mind-blowing. What we're discovering about Pluto is as fascinating as it is unsettling. Far from being an inert frozen world, Pluto is proving to be a world full of mysteries, some of which could challenge everything we thought we knew about the universe. Pluto's heart-shaped glacier, Sputnik Planitia, once thought to be a peaceful, static feature, now holds secrets that may forever change our perception of this distant planet. It turns out that beneath this icy expanse lies a hidden ocean of liquid water, insulated by thick nitrogen ice. This is not just a typical icy landscape, it's a dynamic, active system that churns like a frozen lava lamp. But what's driving this unusual behavior, so far from the warmth of the sun? The answer may lie deep within Pluto's core, where radioactive decay could be generating enough heat to keep the ocean from freezing completely. This discovery is extraordinary for a world located so far from the sun, raising questions about the potential for life in these extreme conditions. In fact, scientists now believe that the very existence of liquid water on Pluto could lead to the possibility of alien life. While Pluto has long been regarded as a lifeless relic, it turns out that it is actually a geologically active world. New images reveal large tectonic features, cracks, and faults across Pluto's surface, suggesting that its crust is flexing and shifting. This level of tectonic activity, so far from the Sun, defies our expectations and invites us to reconsider Pluto's geological nature. Even more astonishing, the massive glacier on Pluto has caused it to shift its alignment with its largest moon, Charon, in an intricate gravitational interaction. This gravitational dance raises more questions than answers. What could be causing Pluto's orientation to change so dramatically? These unusual phenomena suggest that something extraordinary is happening deep beneath Pluto's icy surface. But perhaps the most incredible discovery is the presence of a subsurface ocean on Pluto, which could change everything we understand about the potential for life in the universe. Water is a vital ingredient for life, and finding it on Pluto forces us to rethink the conditions required for life to exist elsewhere. What's more, Pluto's ocean may be even more significant, as it is shielded by several miles of ice and bathed in eternal darkness, creating an environment unlike anything we know on Earth. Any life that might exist here would have to be adapted to these extreme conditions, potentially leading to life forms that are entirely foreign to us. Physicist Brian Cox has suggested that even the simplest forms of life on Pluto would force us to reevaluate our entire understanding of biology. But what if the truth is even stranger than that? What if Pluto's ocean is not just a cradle for life but a home for something far more complex, or even hostile? The James Webb Space Telescope has already detected unusual thermal patterns and chemical signatures that suggest we're dealing with processes we don't fully understand yet. These compounds, which are often associated with biological activity, could be evidence of life forms thriving beneath the ice, or they could point to something far more mysterious. Could these anomalies be signs of life, or are they the result of some other, as yet unexplained process? As we consider the possibilities, we realize that the life on Pluto could be so radically different from anything we've ever imagined that it challenges our very concept of. Recent studies suggest that Pluto came into existence through a series of massive collisions that generated enough heat to allow for the formation of liquid oceans. Over billions of years, radioactive decay in Pluto's core has kept this ocean from freezing, but the impact of this violent beginning might have had lasting consequences. These ancient events could have set the stage for the development of a world that holds secrets beyond our wildest imaginations. As scientists continue to investigate Pluto's surface and interior, one thing is clear: this distant dwarf planet is far from ordinary. It is a dynamic, living world, and the discoveries we make here could reshape everything we know about the formation of planets and the potential for life elsewhere in the universe. But Pluto's surface is not the only enigma. The James Webb Space Telescope has also provided startling new insights into Pluto's thin atmosphere, which is made up mostly of nitrogen, with small amounts of methane and carbon monoxide. This haze is created by complex chemical reactions in Pluto's upper atmosphere, driven by the faint light from the distant sun. These reactions produce organic molecules known as tholins, which give Pluto its reddish tint and add to its mystique. But could these molecules be more than just a byproduct of chemical processes? Could they be precursors to even more complex organic compounds, potentially setting the stage for life? Pluto is not alone in its corner of the solar system. Its largest moon, Charon, plays a key role in shaping Pluto's mysteries. Together, Pluto and Charon form a binary system, where their mutual gravitational influence affects each other in ways that are unique within our solar system. Charon's surface is equally complex, with massive canyons and tectonic features suggesting that it too has a dynamic past. The red polar cap on Charon, which likely formed from methane escaping Pluto's atmosphere and freezing on Charon's surface, points to an interconnected relationship between the two bodies. Could Charon's gravitational influence be affecting the activity beneath Pluto's surface? What role does this close relationship play in the potential for life or other phenomena on these distant worlds? Pluto is just one of many objects in the Kuiper Belt, a region filled with icy bodies and remnants from the solar system's early days. Yet Pluto stands out, with its unique geological activity, its shifting ice fields, and its complex atmosphere. Why does Pluto display such unusual characteristics compared to its neighbors? Could it be that similar processes are occurring on other distant icy worlds, scattered throughout the Kuiper Belt? What we're discovering on Pluto could be just the beginning, offering a glimpse into the hidden dynamics of these far-off worlds. The revelations made possible by the James Webb Space Telescope are just opening a new chapter in Pluto's story, but they've also raised more questions than answers. To truly unlock the mysteries of Pluto, future missions will need to explore the dwarf planet's surface and subsurface with unprecedented detail. NASA's New Horizons mission, which passed by Pluto in 2015, gave us our first close-up look at the dwarf planet, but there is so much more to learn. Future spacecraft will need to delve deeper into Pluto's subsurface ocean, investigate its dynamic atmosphere, and study the chemical anomalies that hint at life. Thanks to new technologies, humanity is closer than ever to uncovering Pluto's secrets and understanding its place in the broader story of our solar system. There's another mystery worth exploring: Pluto's magnetic field. If it exists, it could change how we think about the dwarf planet's behavior and its potential for habitability. While the evidence is still inconclusive, anomalies in the data suggest that Pluto might have some form of magnetic activity. On Earth, our magnetic field protects us from harmful solar radiation and helps maintain our atmosphere. Could Pluto's magnetic field serve a similar function, shielding its hidden ocean and atmosphere from the harsh environment of the Kuiper Belt? If confirmed, Pluto's magnetic field could provide crucial insight into how distant ice